Happy New Year, Data Skeptic listeners. I hope you're enjoying our current series, Graphs and Networks, but I want to tell you about something new today. We're launching a service called Data Skeptic Plus, and just for this launch period, you can actually sign up for free. Maybe we'll keep that, maybe we'll paywall it. Head over to plus.dataskeptic.com. Free account, no credit card required, and once you're logged in, you can listen to all episodes ad-free. You can also try out the first chapter of our new Graphs course, more on that in a minute. If you like what you see and you want to support us financially, for $5 a month or a $50 annual plan, I got 3 immediate benefits coming right at you and more in the future. First, you get a personalized ad-free RSS feed. Drop that into iTunes, Spotify, wherever you listen. No more ads. We're also going to start adding bonus content to the subscriber feeds. Second, you get the first 2 chapters of our Graph course, and you'll get all of them one by one as they get released. We're going to send some subscriber-only merch drops, do discounts on t-shirts in a little bit, and tons more to come. So you got nothing to lose. Head to plus.dataskeptic.com and sign up for your free account. If you like it, support us. You're listening to Data Skeptic, Graphs and Networks, the podcast exploring how the graph data structure has an impact in science, industry, and elsewhere. Welcome to another installment of Data Skeptic, Graphs and Networks. Today we're picking up an interesting topic on a project called Graph Zeppelin that we'll get into. Maybe to start us off, should we define what connected components are? Because I think that's crucial to the work going on here.
Connected components are a basic feature we'll find in any network, it's like the islands in the network. It's the parts of the network that connects to themselves, but don't connect to other parts of the network. Usually, when we look at real-world networks, there are multiple connected components in them. And if we're on the subject, we'll always find a long-tail distribution of connected components. That is, there's the giant connected component, or the GCC, which is the main connected component. We'll see, I won't say most, but a big chunk of the network activity. Around it, many small connected components, which usually when we analyze a network, we usually ignore them. We usually focus on the GCC, the giant connected component.
So a fully connected graph would have one connected component, right?
Exactly.
So I'm thinking of the web or the internet, and my expectation is there's one giant connected component because, most websites share at least one link and everything kind of connects. It would be surprising if there were a lot, at least to me initially, that there would be a lot of connected components. Like, sure, pages in Chinese don't often link to English pages and vice versa. They're separate communities, but there's some links that go back and forth.
Actually, this might surprise you, but I believe that the giant connected component in the internet is like 5% of the internet, perhaps. So
really?
It varies, some say 2%, some say 10%. I'm just giving you the average, right? So
sure.
The reason is there's the concept of deep web that you might have heard of, is the parts of the web that we can't reach because it's not connected. There is no links to it. So most of the web is deep web, and some parts of the deep web are the dark net, right? The dark parts of the network. Sometimes people get confused because they think deep web is the same as dark web, but it's not malicious. It's just how networks are built. There's the GCC and lots of connected components.
So now I think we get the mathematical idea. What is the practical idea? In your role as a network analyst and researcher, when you calculate connected components, what do you use that for? What does it inform?
So usually I don't count them. I get rid of them. I mean, I'm looking for, let's say I'm looking for relevant activity on the network. All the small connected components are usually not relevant. They're not influencing anything. So I get rid of them and I just analyze the giant connected component. But I had one interesting case where I was looking at the brand of a large company, and I wanted to see who are the influencers that are talking about this brand. What I saw was that there's the giant connected component of people, including the brand itself, talking about the product. but there was a big connected component, not a giant one, but relatively big, star-shaped, that one user was tweeting about the product. And lots of people responded. It was a large car company. What the tweet was like, I wish my boyfriend would be run over by this brand of car. So, well, I use it as an example to show how networks can add not only text, but also context. That is, the text is relevant to the car, but the context means that this influencer, she was an influencer, right? She had many replies to her tweet, but it's not relevant. It's not in the context of the brand, what they're looking for influencers that will help people buy this brand.
So I believe connected components in terms of runtime and scalability for a general graph, it's a big O of V squared, where V is the number of vertices. So it doesn't grow exponentially. It's, it can be efficient, but on a big graph, that's going to take a long time to compute, I imagine.
So, this brings us to what David said. And just a sec, I'll look in points. So, I'll start talking about what he said.
Cool.
So, and what he said, he was talking about sketch algorithms that are used to compress graph data and to improve computing time, right? The secret sauce that he talked about in his cube sketch algorithm or graph Zeppelin algorithm is what makes it faster is that it skips a level. Okay, I won't go into details, but this level, I think it was called modular exponentation, which requires more time to compute, especially in large graph streams. So this secret sauce allows the secret sauce allows the cube sketch to find connected components much faster, even on very large and very dynamic large graphs. But there's a limitation though, because the algorithm represents the sum of the edges for each node in the graph only as zeros and ones, it flattens the information you might get from a weighted graph, and so it's limited to specific problems such as detecting connected components where weight of the edge is less important. But as David said to our listeners, give him a nail and he'll find the right hammer.
Right. That actually brings us to an interesting point he raised I wanted to get your thoughts on. He said a lot of research has been on non-dense graphs, so sparse graphs, and that's because there's a lot of sparse graphs in the world, but perhaps it's the case there isn't much research on dense graphs because there hasn't been the tools to approach dense graphs.
Yeah, it's a very interesting point, what I call the mystery of large graphs, and that might be a bias, right? We can guess that there are large graphs that are denser than with the large graphs we usually encounter. The paradox is that the larger the network, the smaller or shorter is the diameter, because there is more chances the graph grows, the more chances there is that a connection would be made between different parts of the graph. According to a study made by Facebook, because we don't have these graphs, right? In 2011, there were about 700 million active users, MAUs on Facebook, and the average distance between them was about 4, which is even shorter than what Milgram in his famous small problem paper wrote, right? That 6 degrees of separation. So here there were 4. And by the way, the giant connected component on this network was 99% of the network, which is very large. What is even more amazing is that in 2016, 5 years later, there were about 1.6 billion active users. That is twice as many users, but the average distance was 3.5. That means that the diameter decreased.
My name is David Tench, and I am the 2023 Grace Hopper Postdoctoral Fellow at Lawrence Berkeley National Labs. Broadly speaking, I am interested in building systems and designing algorithms that help scientists process massive datasets for large-scale scientific applications. In particular, I'm most interested in scalable graph algorithms and algorithms that are randomized and use lossy compression.
What does massive mean? We're in the big data era. What kind of size are we talking about?
It often depends on the scientific application. And so in the context of graphs, this can mean anything that's too big to fit comfortably into a single machine or in the cluster that you have available.
That obviously implies we're going to get into, I guess, distributed computing, or maybe it's high-performance computing. What's kind of the flavor that you take on there?
Oftentimes, graph approaches to distributed computing, when people are trying to solve graph storage problems with distributed computing, their plan is to often deal with the massive volume of graph data by partitioning it across a cluster. So you don't have enough RAM to store your graph in a single machine, so you want to kind of distribute it into multiple machines and then somehow work with that. And so that's something that I do sometimes, but I'm most interested in cases where you're using distributed computing to facilitate compression of data where you're trading off space for extra computation cost. So you're making something smaller, and in the bargain, you have to do a lot more computing. And so in that context, we can do HPC or distributed approaches where the primary thing we're getting out of our big cluster of distributed machines is not necessarily the extra storage, although that can help, but primarily access to lots and lots of computation power that help us squeeze down data into smaller sizes.
In terms of the users of this, like the scientific applications, or maybe customers is the right word, who are the current consumers of this type of work? And if you want to add in people who should be current consumers, that would be good too.
One application we're looking into is particle tracking. So when you have something like the particle accelerators, so we're accelerating protons at really high speeds, crashing them into each other, and then as a result of this, all sorts of particles are flying around a chamber where there are sensors everywhere. And so the sensors notice when a particle moves through them, but they don't know which particle has moved through them. So you have this enormous set of data, which are all these points, and it just tells us that a particle has moved through that location. And one task we have is to try to, what is called trace reconstruction. So the goal here is to identify sets of sensor readings that indicate the path of a single particle that is traveling outward from this collision. And so this is an example of a large-scale graph problem where a lot of the computational work that people currently do here is bottlenecked by the size of graphs that they can represent and work with.
So a moment ago, you described the process of like a compression of the graph, that we could trade off space for compute, but trade-offs usually have some sort of compromise taking place. What's the nature of your trade-off? Hey, Data Skeptic listeners, would you prefer to listen to this show ad-free? Or maybe you just want to support the podcast? Either way, consider signing up for Data Skeptic Plus. That's our new membership program. We've just done a relaunch, and from now till the end of about January, you can actually get a free account. Go to plus.dataskeptic.com. A free account lets you listen ad-free via the web once you log into Plus. And it also gives you access to the first chapter in our Data Skeptic Graphs course. It's free, you don't even need a credit card, you can sign up just to check everything out. If you want to support us, for $5 a month or $50 a year, your Plus membership gets you a personalized RSS feed. That's your own ad-free version of the podcast. You also get the first and second chapters of the Graphs course, and more coming soon, along with a bunch of other bonuses. So if you enjoy Data Skeptic and you get something out of this, check out plus.dataskeptic.com. Trade-offs usually have some sort of compromise taking place. What's the nature of your trade-off?
Well, the first compromise is just these things often are a lot more expensive. There's a technique called graph sketching that when we focus on the Graph Zeppelin paper, I can explain in more detail. But there are several trade-offs we make for this sort of thing. One of them is that to compress all this information often on the fly about a graph that you're given, each time you're given a modification to the graph, you have to do a lot of computation to sort of compress that down into your graph representation. So this is expensive. It's expensive in terms of compute cycles. It's expensive in terms of energy. It's expensive in terms of money. The other compromise we're often making is that algorithms that allow us to do this sort of compression tend to be randomized and approximate. Both are not true of every algorithm, but at least one is true of most of them. So the idea here is that we have algorithms that we can't guarantee will give us the right answer 100% of the time, but maybe we can say with vanishingly small probability, they may fail to give us the right answer. Or we might say, we're sure that they will give us an answer that is close to the optimal answer, but it might be a small multiplicative factor away from the true answer.
So I'm familiar with a lot of, like, let's say NP-complete problems, things that are classically hard to get an answer to. I would definitely accept an answer that's epsilon close to the optimal one if I could get, do that faster. Is that essentially what's taking place?
Yes, although in here, really what we're saying is we're accepting epsilon close answers when we can do them with smaller space. Speed is a consideration, but the primary one is just getting our data down to a size that's small enough that we have a hope of working with it in the first place.
So when I think of a network or a giant graph data structure, it's not clear how I can make it smaller directly. Could you comment more on, like, is it algorithmic or is there machine learning involved? How do you take big and go to small?
Yeah, this is a classic combinatorial algorithmic approach. And there's a bunch of algorithms that do this sort of thing. And I think the best way to answer is to describe one of these algorithms in some level of detail. And I think I'll start by describing the algorithm we look at in the Graph Zeppelin paper. So here, let me set the stage a little bit with the problem we're trying to solve. We're trying to solve a dynamic graph problem. By dynamic graph problem, I mean that we want to compute some structural property of our graph, but the edge set of the graph is changing. So edges can be inserted and deleted at any time, even while we're trying to compute the answer to our graph. So a simple example here is imagine a social network graph where nodes are users and edges are friend relationships. And so to make this more concrete, we can focus on a specific graph problem. So I want to focus on computing the connected components of this graph. We have connected components and our graph can change. And so if an edge is inserted, maybe that connects to components that were previously not connected. If an edge is deleted, it might split a component apart. So prior to the work I'm going to talk about with you today, all of the fastest implementations that compute the answer to this connected components problem where the graph is changing make two key design decisions. The first is they represent the graph losslessly, which means they essentially write down a big list of all the edges in the graph. They might represent it in some clever way, but they're just storing all that information. And the second choice they make is they store that graph in RAM. Now, these are totally reasonable design decisions. They're in fact very common. They're the standard for nearly every large-scale approach to graph algorithms. And for many applications, they work great, but they're also fundamentally limiting. So what if we want to process a graph and get our connected components answer, but the edge set of our graph is so large that we can't fit it in RAM? So either we buy more RAM using the traditional method, either on a single machine or distributed, or we're out of luck. So that's the motivation that we want to look at when we're considering these kind of compression approaches that I'm going to describe to you, to build a solution that helps us when we can't just dump everything in RAM. In this paper, Graph Zeppelin, we are working on an approach to solve this dynamic connected components problem that breaks both of these rules. It compresses the graph down in a lossy way. It doesn't represent it explicitly or losslessly. And so we throw out a lot of information about the graph, but we have a combinatorial randomized algorithm that allows us to guarantee with high certainty that we've only thrown away information that we won't need to compute the answer to the problem. And the second choice we make is that this approach is not just limited to RAM. If the sketch is still too big to fit in RAM, we show how it can spill over out of RAM onto modern fast solid state disks, or in a follow-up paper, onto a distributed cluster without significantly sacrificing performance.
So there's, like, some engineering aspects, some algorithmic aspects. Could you give us a definition of Graph Zeppelin? What does this work encompass?
Our goal here is the input to the system is a stream of edge insertions and deletions that when you take them together define a graph of interest. And so this graph could be changing over time. And the goal of this algorithm is at any moment to maintain a data structure that we can use to query and get back the current connected components of that graph. That's the problem that we're solving. And like you say, there are engineering problems to solve. There are engineering pieces to this effort. And this is a first step towards a much broader set of primitives that you might be able to do. But the key idea and the key thing that makes this system and this algorithm interesting is that we're able to do this using a data structure that is sublinear in the size of the overall input. So whatever the size of the original graph would be, we're using asymptotically much less space than that to compute our answer. And that's the key property of this algorithm that allows us to scale to really large sizes, larger than you could hope to do with any lossless representation of the graph.
And I don't know if it's possible to eloquently sum it up, but what is the secret sauce that gives you that sublinear space result?
Sure. So I'm going to start by describing an algorithm that our work is based on, but was already known in the literature. And then we're going to explain to you the limitations of that algorithm and how we overcame them to make a system that we could actually use in practice. So let's start by thinking about the neighborhood of a node in a graph. So by neighborhood, I mean the set of edges that touch that node, that have it as an endpoint. So we can imagine a picture in our heads of the node and then all the outgoing edges like a many-legged spider. So if we were to record these edges in the neighborhood losslessly, well, that could require space linear in n, the number of nodes in the graph in the worst case. But there's a way to sketch the neighborhood of this graph. And by sketch, I mean we're maintaining an approximate kind of fuzzy picture of this neighborhood that nevertheless captures some important information to us. The metaphor is like, drawing a sketch of a scene that you see in nature. We can form a sketch data structure of this neighborhood that is much smaller than just listing all the edges. So where all the edges is linear space in n, we only need something like log squared bits to store this small sketch. And while we can't, of course, recover all of the edges from this small sketch, we can guarantee with high probability that we can sample one of the edges from the neighborhood of this node. And so that's the picture. So we have this linear sized neighborhood, this many-legged spider, and then we're squeezing it down to only log squared space. The first cool thing about this sketch data structure is that if edges are added to or deleted from the neighborhood of this node, we can update the sketch to reflect that. So our sketch will only return edges that are inserted to our neighborhood and haven't been subsequently deleted, no matter what the sequence of insertions and deletions is. So this allows us to compress the neighborhood information of this neighborhood on the fly as edges are inserted and deleted arbitrarily. The other important thing about these neighborhood sketches is that they can be used to sample across arbitrary cuts in our graph. In other words, if I take a set of nodes and I merge all of their individual neighborhood sketches together into one big mass, then I can query that resulting merged sketch, and this will allow me to sample edges that have one endpoint in my special set of nodes and another endpoint somewhere else in the graph. So if I have learned about a partial connected component somewhere, I can merge all of the nodes for that partial connected component together and use the merged neighborhood sketch to sample an edge coming out of that component into the rest of the graph. In this way, I can grow each of the connected components until I've grown them as large as they can get, and that's when I've discovered the actual connected components of the graph. This is a variant of Boruvka's algorithm for listeners who might be familiar with that algorithm. And so I have this sketch data structure for each of the nodes in my graph, sketching its neighborhood, that is something like log squared or log cubed bits in size. And so I have one of these for every vertex in my graph. So my overall space cost asymptotically is only something like n times log cubed n bits, where, of course, a complete graph or a graph that I'm representing losslessly could use much more space than this.
So I'm familiar with the Bloom filter, and I bet you are too, but for listeners who aren't, it's a probabilistic data structure that uses hashes in a clever way for like membership. Basically, have I seen this particular example before? And it can do some false positives. Sometimes it may say yes when the answer is no, but it'll do no false negatives. Can you maybe frame your technique in a similar context? If there is an error, however unlikely, what's the nature of the error?
Okay, so if there's an error, the error is in the form of the sketch telling you, oh, actually, you've kind of caught me unprepared. At my current state, I'm not actually able to give you an edge coming out of my sketch. That is by far the most common kind of error we get, although those are still very rare. And then there's an even rarer kind of error you can get where you're given an incorrect edge. But both of those failure modes are kind of wrapped into this provably very small error probability. And so you can prove that the probability any of these neighborhood sketches ever go wrong over the entire run of my algorithm is so small that in practice it doesn't really bear worrying about. And in fact, we have experimental evidence to confirm those theoretical results.
Could you expand on that? What are some of the data sets you use for validation?
In the original Graph Zeppelin paper, we use both synthetically generated graphs that were generated according to the Graph 500 specification. They're Kronecker graphs, which is a specific kind of random graph that's designed to mimic certain types of community formation. We also tested with a handful of real-world graphs taken from commonly cited large-scale graph repositories. I think we had like a Twitter graph on there, for instance, and some things like that. And so for this particular question that you're asking about, the correctness or the chance that the algorithm goes wrong in some way, those failure probabilities, which analytically you can show are going to be extremely unlikely, we were actually never able to observe any of them in practice, even after we ran thousands and thousands of trials.
Graph Zeppelin is also like, I guess, an application. I see it's an open source project on GitHub. What does the software do if someone wants to pick it up and run it?
The Graph Zeppelin code base in its current form is designed just for the connected components problem, although we're soon going to release extended versions of these same techniques that work for different graph algorithms as well. And so far, it's relatively combinatorial and very straightforward. You give it either a static graph or a stream of edges, insertions and deletions that define a graph, and it will compute the connected components for you anytime you ask it for an answer. And so you can do this on a static graph, or you can do this on a case where you have a live stream of edges that are coming to you maybe from some data set or maybe from sensors that you have out in the real world. It will maintain the sketch data structure for you and allow you to get the connected components anytime you query it for that.
Well, in any streaming system, there's always sort of an unpredictability. Maybe a pattern could emerge that wasn't there before. Are there any challenges to building a system that handles unpredictable streaming data?
I guess it depends a lot on what you mean by unpredictability, because there's a lot of different ways in which data can be weird. So let me talk through a few of them. The first reason that not the Graph Zeppelin, but this connected component sketching algorithm that I described before isn't practical has to do with this trade-off between space and computation that I mentioned. So again, for each of these neighborhood sketches, we have to do some costly computation every time we want to add an edge or delete an edge from that neighborhood. And it turns out that using the initial algorithm that existed in the theory literature, on the data sets we looked at, each time you want to add or delete an edge, you have to do something like on the order of hundreds of expensive modular exponentiation operations, which are very slow, and they actually, in the implementations we were looking at, they often overflow a single machine word in 64-bit architectures. So this ended up being super, super slow. So the first thing we had to do was come up with a more efficient update algorithm for the sketch. And so we were able to drastically simplify, no more modular exponentiation. Using some hash function tricks, we were able to make this about 3 orders of magnitude faster in practice. But there's another limitation, there's a more interesting one, which is that for certain types of larger graphs, this sketch may still be larger than RAM, even if it is smaller than a lossless representation. And so this is part of why I wanted to talk about this again in response to the question you just asked, because this can sometimes happen when we have unusual or surprising kinds of data coming in through the stream. Even though we've squeezed down our graph size from the initial size to something asymptotically much smaller, in some cases, we can't get it small enough that it'll still fit in RAM on the computer. And so if we try to run the algorithm on disk, which is maybe the first thing you might try to do on a single machine if your data structure can't fit in RAM, because this is a randomized compression algorithm, it turns out to be very slow on disk. It makes random accesses all over the disk rather than the sequential orderly accesses that disks really want to receive to get high performance. But as we were working on this, we realized something, which is that these neighborhood sketches don't just get small space and the benefit of paying this high computational cost. They also have really strong data locality properties, and that allows us to transform our random algorithm that thrashes all over the place into an algorithm that makes large sequential data accesses, and therefore it's very fast on modern disk drives. The intuition for why this is possible is that each of our neighborhood sketches is a compact summary of information about an entire cut in our graph. And so those were the key things we had to solve to go from the algorithm that was beautiful in theory, but maybe not practical, to Graph Zeppelin, which is a system that we could actually build. And we showed in experiments gets something like 10 million updates per second and saves a ton of space on some graphs and can translate seamlessly from the RAM-only computation mode to, if it gets too big, spilling over almost transparently onto disk.
You'd mentioned that the techniques are about 3 orders of magnitude faster in practice. What is that benchmarked against?
That is benchmarked against the fastest existing implementation of the linear sketching primitive that we use to do neighborhood sketching. That is the thing I mentioned that does this modular exponentiation hundreds of times every time you want to change one edge in a vertex neighborhood.
Does that vary by the data set you benchmark on?
No, one of the interesting things about these kind of sketching algorithms, and this is both their benefit and their downfall, depending on the case you're in, is that their performance is remarkably consistent regardless of a bunch of structural properties of your graph. The most important of these is that the space complexity of this algorithm is n times log cubed n, again, where n is the number of nodes in the graph. And notice here that there's no term in that expression that has anything to do with the number of edges in the graph. So it doesn't matter how many edges your graph has, or for the most part, how they are distributed around your graph. The sketch data structure will have the same size. And also because of some of these data movement minimizing algorithms that we implemented for this, also don't really affect the speed at which you can process changes to your graph. This is in stark contrast, I think, to a lot of graph algorithms, which tend to be, in various ways, very sensitive to various structural properties of the graph.
And if a listener wanted to stand up their own Graph Zeppelin instance, what would it take to deploy that?
If you have a machine that's got a couple dozen gigabytes of RAM, and it's got a processor, and maybe a disk if you want to get fancy, you can run basic instances of Graph Zeppelin. In follow-up work, which we recently published in Alinex, there is an advanced version of this graph sketching system that solves more problems than just connected components. And for that to run, you would need a cluster. So you would need to buy some time on AWS or something like that. But for the most simple, our hello world implementation of connected components, which is what Graph Zeppelin is, you can do this on a single machine. We've tried it on a laptop, in fact. I mean, it's pretty computation hungry, so your laptop might get pretty hot, but you can run it.
And do you have a sense from some of the data sets you've worked on about, I guess, error rates? If, you were to get an exact answer for connected components versus the answer the sketching algorithm gives you, we know they're epsilon close. In reality, are there losses or errors at some rate? Do you have any ideas around that?
Yeah, let me clarify something here. When I was describing earlier the random chances of failure and then the epsilon approximation of answers, those are various graph sketching algorithms can have both of those downsides. Connected components will give you the right answer, and then it will fail to give you the right answer with very small probability. But if it gives you the right answer, it's exactly the right answer. There's no notion of an approximate connected component, something that's not quite right. We don't consider that there. If you're any bit off at all, it counts as wrong. And so again, when we ran a bunch of correctness experiments, tens of thousands of them, we were never able to produce any such errors in practice. And that's consistent with what the theory predicts, which is that these things are vanishingly small probabilities of this happening.
And are there any challenges around scalability?
Yeah. So there's the classic scalability problem whenever you're trying to move beyond a single machine and working with graphs, right? Because graphs are notoriously non-local combinatorial objects. Edges that connects a node over here might connect a node completely on the other side of the graph in some sense. And so if you're going to, using traditional methods, if you want to, say, partition the nodes of a graph across a cluster, well, you have a lot of edges that might be crossing different nodes in your cluster, and that's typically quite painful. But one thing that's both a challenge and an interesting benefit of the graph sketching work we do is that these same data locality properties I've mentioned that allow Graph Zeppelin to run quickly on disk, you can modify some of those same techniques to minimize, provably, the amount of communication you need to do between nodes in a supercomputing cluster if you want to run one of these sketching algorithms at larger scales. So the real challenge there is for graph sketching algorithms that get more complicated than connected components, for which we have solved this problem and know how to minimize communication. The trick is how to use these inherently local data locality properties of the sketches to minimize the kind of communication that you would run into across a cluster. And then a secondary challenge is, again, these graph sketching algorithms are very compute hungry. But when you distribute, you suddenly have access to a lot more CPUs and maybe even GPUs. And these sketching algorithms turn out to be super easy to parallelize just because of the way that they're set up. It's almost trivial to do so. So the computational concern, if you really try to scale up and scale out, ends up being less of an issue.
A pattern that some open source projects follow is to provide a related commercial offering. Even though you say, it can be easy to set that up, getting it running on GPUs in just the right way, that can be a lot of headaches for some users, and maybe they just want to allocate some resources and some funds to do that. Do you think there's an opportunity for a commercial product or a commercial version of Graph Zeppelin?
That's an interesting question, and I want to answer it in several different ways. The first, you mentioned the possibility of trying to get something like this a highly parallelizable algorithm working on GPU. So that's actually an active area of research we're working on, is to provide a software framework for this sketching algorithm and then for other graph sketching algorithms that we or other people may come up with in the future, where if you're able to specify the basics of your algorithm, you plug it into a framework that allows you to use GPUs or in general heterogeneous computing architectures, and it kind of takes care of that potentially tricky parallelization for you, because the parallelization patterns for graph sketching tend to be, if you understand them, fairly straightforward. So you can generalize the technique to many different algorithms. But there's another aspect to your question, which is commercial applications of this kind of work, or dare I say in general, any sort of large-scale applications of this kind of work. So there is a commonly held belief among practitioners that work with large-scale graph processing, which is that large-scale graphs are always very sparse in practice. By sparse, I mean that these graphs do not have many edges per node. This belief, if it's true, is kind of bad news for Graph Zeppelin and graph sketching techniques in general, because recall I mentioned that we keep this neighborhood sketch structure for every vertex in the graph that ends up being something like log squared or log cubed bits in size. So if a graph is very sparse, well, maintaining the neighborhood of that node explicitly might be much smaller than that. And then you don't really save space by using sketching. When we started thinking about this stuff, I started wondering, what is the use case for these kind of graph sketching techniques? Where are the graphs out there that we want to squeeze down to smaller sizes that have enough edges to make this work worth it? And this is something you can check out in the Graph Zeppelin paper. We've got a couple of nice plots on this. I looked at all of the publicly available graph datasets on a couple of different repositories of such datasets, so like Network Repository or SweetSparse. So we see that graphs that don't have that many nodes, maybe in the order of tens of thousands or hundreds of thousands, we can see relatively dense graphs and relatively sparse graphs and everything in between for graphs of this size. But when we look at graphs that are larger and larger, all of the graphs at these sizes are exclusively very sparse. And so at first glance, this could support the belief that there aren't any large dense graphs out there. But there's another possibility where when graphs become more than a couple of dozen gigabytes in size, imagine that there were graphs that were larger than that, but if they were more than, say, like 24 or 36 gigabytes or something, we just removed them from the plot. The plot we see is exactly consistent with that. And so this suggests that there may be large and dense graphs out there, but they don't get published because prior to this work that we were doing, recall I mentioned that all of these other high-performance systems store graphs losslessly and in RAM. So this suggests that if they have graphs that were too dense to be stored losslessly in RAM, people just didn't publish on them. In industry, they didn't work with those graphs generally. And so there's a selection effect that means that we only worked on graphs that we had the tools to process, which up until this point was sparse graphs at scale, because we didn't, lossless approaches don't work well on dense graphs at scale. Looking into this a little more, we actually found that there are instances out there, there are examples where some of the big players, say for instance, Facebook mentions in some of their academic publications, that they work with large and dense graph on the orders of, say, maybe tens of millions of nodes and something like hundreds of billions or maybe trillions of edges, if I'm remembering correctly. But they only did this on data that was really crucial to their core operations on huge supercomputing clusters, presumably at great cost, and these weren't data sets that they released publicly. So we see indications out there that there is a need for this sort of thing, but unless you're the biggest player around, you can't afford to process these dense graphs losslessly. And so with the techniques that were out there before we started working on Graph Zeppelin, there wasn't really any hope to make progress on these things. And so we're hoping we can finally put those pieces together and speak to these larger applications.
That selection effect is very interesting, that because the tooling wasn't there, maybe we aren't seeing as much publication about it. Is there perhaps like a simple decision tree a researcher could follow? Someone who has graph data and it's at large scale and they'd like to compute connected components. How should they decide if Graph Zeppelin is the right tool for them?
Okay, so for this specific connected components problem, Graph Zeppelin is most interesting in several cases. The first one, the data you're looking at is truly changing over time. So you have both edge insertions and deletions. If you don't have those deletions in there to mess things up, there are much simpler algorithms that will solve the problem for you, most notably the union find algorithm. But union find doesn't work at all when you're working with live data that might be deleted over time. If you've got large graph data and you have, with the graph representation you're considering, you have many edges per node, so much that you can't fit it into RAM, and it's live data so that the edges are being inserted and deleted over time, then Graph Zeppelin or some of the systems we're working on based on it might be the right choice. We have other graph streaming work that can give you benefits even in cases where you're not deleting edges, but those are for more complicated combinatorial problems than connected components.
Well, if you look to the future, maybe beyond connected components, what are some of the other algorithms or questions that you think these techniques could help solve?
There's a lot of exciting work in that direction, and so I want to go back and mention this particle tracking application again. And so we think that the right tool at a certain part of the workflow for this particle tracking application, I won't get into all the details, but at some point they're dealing with graphs that are too large to manage for the next stage of their workflow. And they want to do some sort of clustering algorithm. This is near the end when they've got a graph that represents some noisy guesses about which particle trajectories might map to which sensor hits from these particle collisions I was mentioning earlier. And so the last step of what they want to do is some sort of clustering method. There are graph sketching and streaming algorithms that do what is called spectral sparsification, which you can think of as an extremely generalized version of preserving all of the graph cuts in the algorithm. So connected components is a related but much, much simpler problem than this. And in fact, these spectral sparsification algorithms not only preserve all the graph cuts in the algorithm, but some other spectral properties of the graph as well. And so the downstream effect of this is that you should be able, if you're given a graph that has some sort of optimal clustering, you can end up with a much sparser graph that if you run your same clustering algorithm on it, it will give you an epsilon close clustering by some clustering metric. And so this is a case where you throw out a bunch of information about this graph at this point in the particle tracking workflow, and what you end up with is a much sparser graph that you can actually cluster. And the answer you get is pretty good. Maybe not, as good an answer as you would have been able to get had you been able to process the original graph. But the problem is that one was too big for you to do anything with anyway.
So feel free to disagree, but I think I would describe your approach as something that's algorithmic, and as a result, we get some asymptotic guarantees. On the other hand, there are things like graph neural networks and embeddings that rarely have those guarantees, but are often kind of magically really good at solving problems. Do you have any thoughts on how AI might be an alternative approach, and if that'd even be useful?
It's interesting you mentioned that because in this particle tracking application I mentioned, there's a different part of that same workflow where they are using graph neural nets to kind of pre-process data that you'd later want to cluster. And so honestly, I see the sort of machine learning based approaches and then the combinatorial or algorithmic approaches that I work on as friends and not competitors, in the sense that they are good at different things. So often for the kind of, even connected components as a combinatorial property of a graph is very fragile. If you just sample a bunch of edges kind of randomly from a graph, you may not get the connected components of that graph. You need to do a very specific and combinatorial kind of sampling to make sure that you get that, right? Like imagine that there's only one edge in a very densely connected graph that connects two pieces of it. Well, you need to randomly sample that edge, which is unusual unless you do special things. And so a lot of machine learning approaches work great in certain kinds of high dimensional data where you can come up with general broad statistical patterns that you can make inferences from. But these really fiddly structural combinatorial graph properties, I think they often struggle to get good answers for. But again, I see them as friends and not collaborators. So in workflows, you often have, you often want to do these sort of graph structural properties as a pre-processing or post-processing step after you've done some sort of graph neural net or other graph-based machine learning on some application. And so you might do, like the goal of these small space lossy compression graph algorithms is to maybe make things easier on your GNN by giving it a sparser input that's easier to learn things on, or to summarize information that a GNN has given you as output into something that is more manageable, but still contains the signal that the GNN returned.
What do you see as the future for Graph Zeppelin?
My vision is that Graph Zeppelin is a proof of concept and the first step towards a new way of thinking about processing large graphs. I made a case earlier in our conversation that there is this big gap in the problem space that people have never explored because we didn't have the tools to address it. All graphs that are large, but not super, super sparse. And combinatorially speaking, these graphs, like this unexplored area of the map of the problem space of graphs, is the overwhelming majority. We've been exploring a tiny, tiny piece of the puzzle here. One of my hopes is that as we continue to build more algorithms, more effective algorithms that scale up and scale out better, we will start to see what applications and what cool graph structures are lurking out there in those unexplored wilderness that encompasses most of the graph problem space. Like I said, I think Graph Zeppelin, I'm hoping, is the first step in that direction. And so we're working on a bunch of follow-up work that involves tackling different kinds of graph structures. Can we compress them down into small forms so that we can work with them even if the graphs are truly massive? And then thinking about, like I mentioned before, frameworks that would allow people to come with their own sketching algorithms and apply them to problems that they think are of interest. After they've specified the basic algorithm in code, this gets applied to a framework that can be run on a GPU or a cluster to help with scale out.
And where do you think we are on the, adoption curve? Earlier, we'd hinted that maybe a lot of these problems were only taken on in big companies where there was a lot of resources available. What does the next maybe 5 to 10 years look like in terms of adoption of these techniques?
That's a really good question. It's one I wonder about a lot because I think we're very, very early on the adoption curve here, right? Like, we're just starting to understand, even for the most basic of these algorithms, what is required to make them practical. And so I think there has been very little exploration of this unexplored area of the map up until this point. And so it could go in a bunch of different directions. I think it's really too early to say. At this point, the attitude I'm taking is what one of my collaborators calls the field of dreams approach. If you build it, they will come. And so we're starting to build capabilities that we suspect are going to be useful for large-scale applications we know of. And our goal is to take those to stakeholders in academia and industry and say, hey, is this what you need? Does this lossy compression algorithm help you address a problem in your workflow? And so we're starting to do that. We have a couple of hopeful starting points, but I think it is really too early to say much. Other than I'm sure that they're out there somewhere. They kind of have to be, because the only other explanation for that suspicious plot I mentioned earlier is that the graphs that we see in nature are actually a function of how much RAM we have available, which doesn't seem right. So there's got to be something out there, right? And I'm just excited to explore and find out what we can find.
David, is there anywhere listeners can follow you online?
Yeah, I very occasionally post on Twitter. My handle is David Tench _. That's it. I mean, I post papers on Archive, but I'm not super active on social media or anything like that.
Sounds good. We'll have some links in the show notes then for listeners to follow up.
Oh, actually, sorry. One more thing I just thought of, which is, as I'm talking about exploring this unexplored part of the problem space, we're really interested in hearing from customers of graph applications of all stripes. So if you have a large-scale graph application that you don't currently have the capacity to deal with using your current methods and your current hardware, even if it doesn't sound like the techniques I mentioned today, drop me a line either on Twitter or you can go to my personal website, davidtench.com, and get in touch with me, and we'll see if we have a hammer that can help you with your nail, or if we can design one with you.
Very cool. Yeah, I hope some connection comes of that. David, thank you so much for taking the time to come on and share your work.
Yeah, thank you. This was a lot of fun.